Now let's talk about Huffman code and transversing trees. The primary purpose of a Huffman code tree is, well, remember the idea was to make it so that the characters that were used more often, you had fewer binary digits to represent it. So for example, in this tree shown to the right here, we've got A and T that are used. So we have A and T that must be most common in whatever string we're coding with this Huffman code tree. So A and T must be probably the most commonly used, so they're pretty high up. D and H not used very often, so that's the reason why they're closer to the bottom. Well, because of that, what we're looking at is data compression is in fact the primary purpose of these Huffman code trees. So let's take a look at this tree in number 28 and see if we can't encode the word haunt using the tree. Well, in order to get to H, we have to go down 1, 1, 1, 1. So 1, 1, 1, 1 are the first 4 digits, which give us the first character. All right, next letter is A. Where are we going to go for A? Well, in order to get to A, we have to go down 0 and then go down 0. So that will be 0 and 0. Next letter is U. Well, U is down here, and to get to U, we have to traverse 1, 1, 0. So 1, 1, 0. To get to N, we have to go 1, 0, 0. 1, 0, 0. To get to T, we have to go down 0 and then 1. So 0 and then 1. So this string right there, that's what you need to follow or traverse in order to spell out the letters in haunt with this encoding. Let's take a look at number 29. Now 29 wants us to go the other way. We've got this string of ones and zeros. What does it translate to whenever it comes to our... Let's uncover the A. What does it translate to whenever we use this Huffman tree? All we have to do is simply follow the path based on the characters in this string until we get to a letter. And once we get to a letter, we write that letter down, and then we go back to the root and start over again. So we start out, we go 0 and then 1. And so 0 and 1 brought us to a T. So we've got our T. And we get to this point right here. Next, we go down 1, 1, 0. So that's a U. And by the way, this is not necessarily going to lead us to an actual word, but 1, 1, 0 brought us to there. Now we have 1, 0, 1. That brings us to an R. Brings us to there. And then we have 1, 0, 0, which gives us an N, and that brought us to here. Now we have 0, 0, so that brings us to the A and brings us to this point in the code. Then we have 1, 1, 1, 0, which brought us to D. Now, ternad is not necessarily a word, but that's what that sequence has encoded. All right? All right, next we're moving on to problem number 30. And 30, 31, and 32 all talk about the order in which we visit the nodes or vertices of a tree based on whether it's pre-order, in order, or post-order. Now, remember, there was that trick. Yes, you could remember the process. You first, for example, for a pre-order search, you first visit the parent, then you visit the child to the left, and then you visit the child to the right. Well, if the child to the left has children, you first visit it, and then you visit its child to the left, and then you visit its child to the right, and so forth. And so you get this order of vertices that you visit, or this order that you visit the vertices. But I gave you a shortcut that I'm going to use right here, and that was the idea that you make a path tucked into all the nooks of each one of these trees, or each one of these branches, and make a path around all of the vertices of the tree. Now, each one of the vertices is passed at least once, maybe twice, maybe 3 times, depending on its position in the tree. For example, B is passed 1, 2, 3 times. Depending on which type of order you're visiting these nodes, you will visit each one. So let's start with pre-order. Now, pre-order says that we are going to visit on first pass. All right, so as soon as you pass it the first time, you visit it. And so we visit, but you remember, none of these do you visit twice. You only visit each one once. So in the case of a pre-order search, we're going to visit A first. We pass A first, and then we pass B, and then we pass D, and then we come up. We've already passed B, so we don't pass it again. The next one to pass is E, and then we come down past F. All right, then we come up. We've already passed E, don't do it again. So we pass G, and then we pass E. No, we don't visit it again, though. We pass B, don't visit it again. We pass A, don't visit it again. And then we pass C on its first visit, so it's C is the next one we see. So the order on pre-order search that we visit each node of this tree is A, B, D, E, F, G, C. That's all 7 of our nodes. That should be a complete traversal of the tree for a pre-order search. Let's move on to in-order search. In-order search says that we visit a node. Well, it's kind of interesting. We have 2 different things. We visit leaf on first pass. Then we visit parent on second pass. This will make sense if you understand the actual visiting order of the nodes whenever it comes to an in-order search. What you do with an in-order search is you visit to the left first. So if I start at A, I visit to the B to the left first. And then once I've fully visited B, including all of its subtrees, then I visit A, and then I visit to the right. So for an in-order search, it's left, parent, right. Now, that process turns out that whenever it comes to using this little shortcut is just simply visit the leaves on the first pass and visit the parent on the second pass. So let's visit this tree in an in-order search. So A is a parent, so we don't visit on the first pass. B is a parent, so we don't visit on the first pass. But D, that is a leaf, so we visit it. Now when we come back up, this is our second pass of B, so we go ahead and visit the parent B on the second pass. E, this is our first pass, and it's a parent, so we don't visit it. F, we visit, because it's a leaf. Then we have our second pass of E, so we visit it. Now we visit G, because it's a leaf. Come back up. We've already visited E, we don't visit it again. We've already visited B, we don't visit it again. A, this is our second pass of A, so we visit it. And then on our way down, we visit C, which is a leaf, and we get D, B, F, E, G, A, C. That's all 7 nodes of this particular tree visited in an in-order search. Now, last, we have the post-order search. And the post-order search, well, it's the exact opposite of what we had with the pre-order search. We visit on last pass. All right, and this includes the leaves and the parents and the internal nodes. So I'm coming around here. There's my path, right? This time, we just keep track of the last time we passed something. So we come down and don't visit A, don't visit B, but D is a leaf, so we go ahead and visit it. Then we come up, B is our second pass, but we'll have another one, so we don't visit B. And then we come down to E, it's our first pass, we will have another one. F is a leaf, so we visit that. Come back up, E we will visit again, so we don't visit this time. And then we have G, our last visit of G. And then we come up, here is our last visit of E. And then we have our last visit of B. We pass A, but we don't visit it because we've got another one coming. Then we have a leaf C that we visit. And last of all, we visit A. And so we get this order of nodes in a pre-order search, D, F, G, E, B, C, A. And that'll give us all of the passes for this particular for this particular tree. Now, 33 and 34 are actually the results of in the case of the prefix notation, it's the results of a pre-order search of a tree that represents a mathematical expression. Now, a mathematical expression represented with a tree usually has an operation as a parent, and then the children of that are either another operation or an actual value, a number. If it's an operation, well, that operation is going to have children too, and those guys are then going to have numbers or other expressions as their particular as their children. So this tree that I've just sketched in the lower right hand corner here is, as you look at this in an in-order search, it would give you 3 times 2 plus 5. But notice that in this case, we don't have a worry about order. Well, we do have a worry about order of operations, but the order of operations that is defined by this tree is missing the parentheses. Now, just because multiplication has precedence over addition, we didn't really need the parentheses, but that may not always be the case. We may have the plus and the times swapped there, in which case we would have had a different operation without the parentheses. So anyway, when you look at an in-order search, you need parentheses. But whenever you're talking about a pre-order or a post-order, you don't need to have the parentheses. All you're looking for is a specific pattern. And in the case of a prefix, you're looking for this operation number. Now, there's only one of those patterns in this full string, so we can only do one operation. And basically what you're saying is the 5 minus 3, that should be inside of parentheses. So we compute 5 minus 3, and we get 2. Now, we also, though, have to copy down the rest of the string on either side of that operation. So you have the plus 4 times plus that comes before the result of the 5 minus 3. And then after the 5 minus 3, you also have to copy down the 2 and the 2. Note that each one of these integers is to be treated as a single integer. This is not 53 and 22. This is a 5, a 3, a 2, and a 2. Now, if you look at our new string, you'll see that we have the pattern again. We have an operation followed by a number followed by another number. And so in this case, we're going to do the plus 4 times and then replace the plus 2 with 2 plus 2, which is 4, and then drop down the 2 right behind it. Now, this plus 4 times 4, 2, notice that we have this format again, operation number. Well, that is going to be replaced with, we'll drop down the plus and the 4, that's going to be replaced with 4 times 2, which is 8. And finally, we have one last application of this pattern, the operation number, and this gives us 4 plus 8, and that's equal to 12. So the result of this string, written in prefix notation, is 12. Now let's take a look at the next one. The next one is in postfix notation, which means we're going to look for a slightly different pattern. In this case, the operation is going to come after the 2 integers. So we have in this string in postfix notation 2 patterns that we're looking for. Number operation in 4-2 divides and number operation in 5-3 plus. So we compute 4 divided by 2, that's 2. We compute 5 plus 3, that's 8. And we copy down the rest of the string, inserting 2 and 8 in the appropriate positions. So we have 5, and then we have a plus, and then we have a 3 minus times. Now, notice we once again have the number operation in 2 places. We have 5 plus 2 and 8 minus 3. Well, 5 plus 2, that's 7, so we replace that 5 plus 2 with 7 in our string. And then we have 8 minus 3, that's 5, so we replace the 8 minus 3 in the string, or the 8 3 minus, with 5. And that leaves us with the multiplication operation. And finally, we have number operation in 7-5 times. And so we do 7 times 5, that's 35. That gives us our answer. Now, it's important to understand that if you get to a point where you have a string that doesn't have this pattern, it means one of two things. Either the number of the operation or the expression was not written in appropriate postfix or prefix notation, there was an error, or you made an error in the substitutions as you worked your way through the string. If the string is appropriate, you will always get a final value or a final result for the expression.